Last year, nearly 38.2 billion tons of carbon dioxide were pumped into the air from the burning of fossil fuels such as coal and oil. But scientists have come up with a way to convert the gas into a more useful product, ethanol. The researchers stumbled upon the simple reaction by accident. But if the process could be scaled up to industrial size, it could help to reduce the effects of global warming. Scientists at the Department of Energy's Oak Ridge National Laboratory developed an electrochemical process that uses tiny spikes of carbon and copper to turn carbon dioxide, a greenhouse gas, into ethanol. Dr. Adam Rondinone, lead author of the study, said, "We discovered somewhat by accident that this material worked. We were trying to study the first step of a proposed reaction when we realized that the catalyst was doing the entire reaction on its own. You can use ethanol in the current vehicle fleet right now with no modifications," he added. The researchers created a catalyst, a substance that increases the rate of a chemical reaction made of carbon, copper and nitrogen. When voltage was applied, the catalyst triggered a complex chemical reaction that essentially reverses the combustion process. With the help of the catalyst, the solution of carbon dioxide dissolved in water turned into ethanol with a yield of 63%. Without the catalyst, this type of reaction normally results in a mix of several different products in small amounts. Dr. Rondinone said, "We're taking carbon dioxide, a waste product of combustion, and we're pushing that combustion reaction backwards with very high selectivity to a useful fuel." Ethanol was a surprise. It's extremely difficult to go straight from carbon dioxide to ethanol with a single catalyst. What makes the new catalyst unique is its nanoscale structure consisting of copper particles embedded in carbon spikes. This novel texture avoids the use of expensive or rare metals and would make scaling up the catalyst a realistic goal. Dr. Rondinone said, "By using common materials but arranging them with nanotechnology, we figured out how to limit the side reactions and end up with the one thing that we want: the combination of low-cost materials and the ability to use the catalyst at room temperature in water means the approach could be scaled up for industrially relevant applications. For example, the process could be used to store excess electricity generated from wind and solar power sources." Mr. Rondinone added, "A process like this would allow you to consume extra electricity when it's available to make and store as ethanol. This could help to balance a grid supplied by intermittent renewable sources." The researchers now plan to refine their approach to improve the overall production rate and further study the catalyst's properties and behavior.